Hello, I'm Sinead. I'm a PhD student and member of the Low Temperature Plasma Group in the Centre of Plasma Physics at Queen's University Belfast. Our collaborator on this project is Professor Tomoyuki Murakami of the CK University Tokyo. My poster today will be at our project entitled Simulation of Atmospheric Pressure Plasma Jets using Finite Element Method. Over the last 20 years, there has been an increase in the use of non-thermal or cold atmospheric pressure plasma jets. Plasma jets are used routinely in material processing and biomedical applications. Atmospheric pressure plasma jets are sources of chemically reactive species that can be operated at room temperature and pressure for a wide range of applications. The plasma jet consists of a helium gas flowing through an open dielectric tube into air at atmospheric pressure and room temperature. Gas flowing through the quartz tube is excited by the pulsed voltage given by the copper electrodes that creates the plasma. Adding a small impurity to the noble gas produces the chemically reactive species. The flow rate of the working gas or the electric field geometry determines the length of the plume. Atmospheric pressure plasma jets can be thousands of Kelvin in the tube, but the plasma jet itself can have temperatures of a few hundred Kelvin, making it ideal for biomedical applications. Non-invasive healing is no longer just science fiction. Plasma jets can be used as an alternative treatment for cancer, used in wound healing and for sterilisation. They do this by producing charged particles, electrons and ions, neutral metastable species, radicals, electric fields and UVU and ultraviolet photons. The plasma cocktail not only triggers a variety of cell responses, cell detachment and apoptosis, but also at a temperature that does not damage skin and tissue. In fact, our plasma jet setup in Queen's has shown to be very effective in bacteria inactivation. As you can see, the biofilm in the photo on the right has been greatly reduced after being treated with the plasma. So a plasma fluid simulation with the 2D finite element method is being used to model our plasma jet. COMSOL works by solving a series of partial differential equations. The fluid equation describes the electron number density, the mean electron momentum, and the mean electron energy as a function of configuration, space, and time. The rate of change of electron density is described here, and the equation is a partial differential equation for electron energy density. Poisson's equation is used for the electrical potential. Here are some variables used in our model. COMSOL needs an initial electron density and electron energy to start off the electron energy distribution function. We use secondary electron emissions of 0.1 and excitation frequency of 20 kHz at atmospheric pressure and room temperature. We use an axisymmetrical 2D model in cylindrical polar coordinates. The geometry is based on the real jet, with copper grounded and powered electrons here and here. The tube is made of quartz and the helium flows from the top. The jet plume is released into the helium atmosphere. Our experiment uses a pulse decaying power input. It is an applied peak-to-peak maximum of 6 kV with an RF frequency of 20 kHz. We believe this may be a unique power source for a plasma jet. We were able to simulate the decaying sinusoidal waveform in our model. I'll go quickly now through some preliminary results from our model now. The gas velocity can be determined from the gas flow rate and the tube diameter. The gas density changes with temperature and the flow is laminar. We have electrical properties of the plasma, the electrical potential and the electrical field in the R and Z components. The lines represent individual pulses. Note the voltage is higher at the powered electron site. This corresponds with the 6 kV applied voltage. Here is an animation of the plasma properties, which is time-dependent behaviour of the model. Electron density on the left and the metastable 23S on the right. They are all on the log scale. Note that the pulses indicate the pulsed input voltage. This is over a 2 millisecond time scale. Note that the metastable has a higher density and a longer jet owing to its longer lifetime. Some results now of the number density and electric field components taken at the jet exit. Note that the separate R and Z field. They diminish the further away from the tube exit. As expected, the helium Xmer is to have the highest density due to its longer lifetime. And here is the reaction rate at the tube exit for reaction sets of ground state helium, helium ion, and metastable 2,3S. So lots of work needs to be done before we can validate or benchmark our model. We have to add oxygen and nitrogen. We can use targets and change the parameters such as power supply, the gas flow rate, and change the electrode arrangements. We can use our model to optimize our plasma jet to be used in 6 bays of the future. Thank you for watching, and please come and see me in the breakout room tomorrow.